Hi, welcome to this video. My name's Phil and I'm a senior lecturer in astrophysics at the University of Lincoln, and I'm going back to galaxies again for this video. But this time around I'm going to be looking at elliptical galaxies and also what the differences are between a chord elliptical galaxy and a coreless elliptical galaxy. So we're kind of looking at a bit more of the specific technical details, differences between a particular type of galaxy. Now, if you're not familiar with what a galaxy or what galaxies are, these are generally massive systems of stars, gas, dust, also dark matter. They're gravitationally bound together, so some of those are actually rotating like a disk, some of them are more spherical. So they come in a variety of shapes, sizes and compositions. So some of them contain more or less gas, dust and that sort of thing. So for example, elliptical galaxies have less gas in them than a spiral galaxy. They are typically can be much bigger than a spiral galaxy, and you've also got that dark matter there. But anyway, these are massive systems comprised of the stars and all the other material as well. Now, they do come in lots of different shapes and sizes. Some of them are fairly predictable. So disc-like galaxies are kind of like disc-like. They're kind of rotating around like a disc. You've got elliptical galaxies, which are more spherical. These have more random-like motions of the stars within. And you've got irregular galaxies, which don't have a regular shape. They can be different. They're normally distorted for some reason or another. So a whole variety of different sizes and shapes of galaxy. Now, the two main types really are spiral galaxies, which sit on the right-hand side of the Hubble Galaxy Classification System. Again, you've got two tuning fork pathways there, I suppose. The top branch is for normal spirals with a spherical bulge in the centre, whereas the bottom branch is for barred spiral galaxies, like our Milky Way actually. And in the middle, sometimes there's an intermediate one where you've got like weakly barred spiral galaxies. And then on the other side, you've essentially got your elliptical galaxies. So these are the two main types. Now, there are other sorts like irregular galaxies, peculiar galaxies, dwarf galaxies, all those sort of things, and also lenticulars. But the two main types are your spirals and your ellipticals. And these are on the left-hand side, and these are mostly classified by their shape. So an E0 elliptical galaxy is mostly spherical, whereas the E7 is going to be more cigar-shaped. And again, these have less gas content in than a spiral galaxy. They don't rotate as a complete, well, they don't have a net rotation, I should say, although some do. It's generally quite weak. They don't have recent star formation, so they can be quite red because they've got old populations of stars, basically. And they don't have any features like spiral arms. But these are the ones we're interested in for this particular video, elliptical galaxies. Now, in the previous video, I kind of looked at the bulges of galaxies. So in the central part, there's a higher density of stars, and there's a few different sorts of bulge that you can kind of get. But we're going to go a little bit further than that now. We're going to actually have a look at this central region of elliptical galaxies and look at the distinction between chord and coreless elliptical galaxies. So, when we look at elliptical galaxies, we can essentially put them into two sort of categories, really. So again, we're looking at the bright, not necessarily the bright, I suppose they are bright actually because they get brighter towards the centre. We've got these central regions which typically have a higher density of stars, which kind of makes them bright. So now we're considering this part of ellipticals. Now what we can do, or what we typically do with galaxies, is we measure their surface brightness as a function of the distance from the centre of the galaxy. And this is called the surface brightness profile. And when we do that with elliptical galaxies and spiral galaxies actually, it typically decreases as you get further out from the centre. What that basically means is you've got a higher density of stars in the centre, stars emit light, so it's brighter basically. So generally it kind of drops off, and we can normally model that with the kind of Sir-6 index. And it'll have a particular value for that. It's like an exponential drop-off, or can be. And we can tweak that shape depending on the type of galaxy. So the Sir-6 index is helpful for that. But as a general rule, the surface brightness profile tapers off and drops off as we get further towards the outer part. So if we were to look at the brightness profile in the center part, we can actually distinguish between two types. We've got the chord type and the coreless type. We're going to have a look at what the differences are, and they're kind of relatively subtle. So the outer parts still follow that same surface brightness profile for a fairly typical elliptical galaxy, but when you get to the center, they deviate, and this is what puts us into these two classifications basically. So a chord galaxy shows almost a near constant brightness at the centre. So when we get towards the centre part of the galaxy, the brightness doesn't keep on increasing. It kind of almost, it doesn't go perfectly flat. There is still some small increase in brightness, but it kind of levels off. It's a very small increase in brightness. So chord galaxies, they're almost kind of like missing light, I suppose is the best way. They have a constant brightness. They're not constantly increasing. What that's telling us physically is that the density of stars doesn't significantly increase towards the centre. So as we get towards the centre, the stars, the density of the stars does not massively increase. So physically, that's kind of what we expect to happen here. So chord elliptical galaxies then, as a general rule, we find chord elliptical galaxies to be generally higher in total luminosity than maybe a coreless one. So these could be much bigger galaxies. So total higher luminosity. There's a central light deficit. So because they kind of go almost constant in their light profile, there's light missing there. There's less density of stars. So they have a central light deficit, and the light distribution is fairly smooth as well. Now the coreless ones are kind of the opposite. What happens here is we see an excess of brightness in the centre. So as you get closer to the centre, they deviate away from that typical profile we would expect for the decrease in brightness as a function of the radius. As you get close, it kind of moves above that line, so we have an excess of brightness at the centre part. This is the opposite to a chord galaxy. And what that's physically telling us in this situation is that the density of the stars actually increases significantly as we increase towards the centre of the galaxy. So to get closer in, then the stars get denser. And if there's more stars there, they emit more light, it appears brighter basically. So they're generally lower luminosity galaxies. These particular galaxies that are coreless are generally smaller elliptical galaxies. They will show a central light excess, and because they're smaller, they can also be more disc-like as well. So these particular ones do show a bit of a flattening, a bit of a rotation compared to the larger, more spherical elliptical galaxies. Now, why would we have these differences between these two types of galaxy? Well, part of it could be related to their merger history. So here we've got a galaxy merger tree, which I've done a separate video on again, and it could be related to wet or dry mergers, with one of those producing a chord and the other a coreless. And that's because a wet one, you have two galaxies that will have high gas content in them. That would be classified as wet. Why is it classified as wet? Well, when two galaxies with gas in them collide and merge, you get a sudden increase in star formation. If you have a dry merger, it means there's no gas there. You don't get an increase in star formation, there's no gas there. And that can impact what's happening in the centre. Like if you've got a dry merger, you don't get an increase in stars. But if you had a wet one, you would. So if we've got an excess of light, then that can help explain why. We might have a sudden increase in star formation, which can then give us that excess amount of light. It can also relate to the central black hole as well. So we have a large central black hole in most galaxies actually. Sometimes we can have binary black holes, and they can impact the dynamics that's occurring in the centre part. And that can then impact, again, the brightness and the luminosity in the centre parts of these galaxies. So it could be a combination of things that are essentially going off with these galaxies. But thank you for watching. If you enjoy the videos and find them helpful, then do consider becoming a member. There's extra videos in the members section, but it also helps support the channel. So thank you for watching.